Given a matrix A, let's say A11, A1n, AM1, AMN, then we already know how to compute a basis for column of A, a basis for row of A, and a basis for null of A. Remember, what we do is we do row reduction. We get a matrix B, and then in this matrix B, we select those columns that has a pivot. Then columns with pivots, and then this column with pivot, we go back to the original, and then we select those columns, and then these columns here, columns in A that goes with the pivots of B, they form a basis for column of A. Also, we just take the rows here that are non-zero rows, and they form a basis for row of A. And to compute null of A, we just set up this system. Let's say we just solve the system, and since we already have this in reduced echelon form or in echelon form, then we can solve this system, and then we will get that what we call the generators of the solution is going to be a basis for null of A. Notice that the dimension of null of A is just the number of free variables, and the dimension of these two is just the number of basic variables. When we are thinking about the homogeneous system given by A. But let's suppose that we have a slightly different situation to represent the subspace. Let's suppose that W is equal to the set of vectors of the form A plus 2B plus C, A minus B, C plus D minus B, such that A, B, C, and D are real numbers. We can check that this is a subspace, but then in order to find a basis for this subspace, we just rewrite this subspace in this form. We factor the A times 1, 1, 0, plus B times 2, negative 1, negative 1, plus C times 1, 0, 1, plus D times 0, 0, 1. And then we get that this subspace, such that A, B, C, and D are real numbers. But then we get that this subspace is just the span of these four vectors. 1, 1, 0, 2, negative 1, negative 1, 1, 0, 1, and 0, 0, 1. But that means that this subspace is just column of A if we define A to be equal to this matrix 1, 1, 0, 2, negative 1, negative 1, 1, 0, 1, and 0, 0, 1. And we already know how to compute the null of A. We have to do row reduction, and we select those columns that goes with the pivots of the matrix that is in reduced echelon form for this matrix A. Then we can move from here to this problem that we already know. Also, if we have a subspace that is given like this, let's suppose that we have W equal to x1, x2, x3, x4, such that 2x1 plus 3x2 minus x1 plus x4 equals 0, and x3 minus x4 equals 0. Then, to find a basis of this subspace, we define this matrix A equal to the matrix 2, 3, negative 1, 1, and 0, 0, 1, 1. And then we notice that essentially this subspace W is just the null of this matrix, and we already know how to compute the null of a matrix. Let's do another example. Let's suppose that we have a subspace in the space of polynomials. Let's suppose that we have the span of these polynomials. How do we find a basis for the span of these three polynomials? One way to do it is just to create linear combinations to check if these vectors are linearly independent. Notice that if these vectors are linearly independent, then they form a basis for W. But let's do that. Then you do in the process alpha 1, 1 minus x plus x squared, plus alpha 2, 2x cubed plus x squared minus 3x plus 3, plus alpha 3, x cubed minus x plus 1 equals to the 0 polynomial. Then we set up the equations and we get the coefficients of 1, the coefficients of the constant numbers. We have alpha 1. Here I have plus 3 alpha 2. And here we have plus alpha 3 must be 0. The coefficient of x, we have negative alpha 1 minus 3 alpha 2 minus alpha 3 equals 0. And then we have the coefficient of x squared, alpha 1 plus alpha 2 equals 0. And then the coefficient of x cubed, we have 2 alpha 2 plus alpha 3 equals 0. And then we have that the augmented matrix of this system is 1, 3, 1, 0, negative 1, negative 3, negative 1, 0, 1, 1, 0, 0, 0, 2, 1, 0. And this is row equivalent to the matrix 1, 0, negative 1, half, 0, 0, 1, 1 half, 0, 0, 0, 0, 0, and 0, 0, 0, 0. When you think about this, that means that x3 is free, and since x3 is a free variable, that means that if you pick x3 to be equal 1, then you can create a linear combination where x3 is equal 1, and that means that you can solve for this polynomial as a linear combination of these two. These two polynomials corresponding to columns that has pivots here, that means that these two polynomials are linearly independent. Then what is happening is something similar to what happened in the case of computing the space of column of A when A is a matrix. Then we just write a linear combination and we make it equal to 0. That gives us an homogeneous system, and then that homogeneous system has an augmented matrix. We do row reduction, and then we see what columns have pivot, and then we select those polynomials that goes with those columns. Then in this case, that means that a basis for W is just this set, the set of, with this vector, 1 minus x plus x squared. Remember that we call it vector because this is contained in P3, polynomial of degree 3 or less, and this is a vector space, and elements in a vector space are called vectors regardless if they are polynomials or matrices or anything else. Then here we have this and this. These two elements form a basis for W, and that means that the dimension of W is 2. We can also do the same trick for matrices. If we have W is the span of these matrices 1, 2, 0, 2, 1, negative 1, 1, 3, 2, 1, 1, 0, 1, and 4, 0, 1, 1, negative 1, 2. Then if we want to compute a basis for W, then we can just set up a linear combination of these matrices equal to the 0 vector. And then we get a homogeneous system and it has an augmented matrix. We do row reduction and we get, let's say, a matrix in echelon form. And in this case, we select the pivots of this matrix, and those pivots corresponds to the matrices that we need to pick from here to make up a basis. In this case, if you do the math, you will get that this matrix is the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. We have six equations because we have 1, 2, 3, 4, 5, 6 equations and 3 variables, and that means that these 3 matrices are linearly independent, and therefore a basis would be just these 3 matrices without the span, right? Just these 3 matrices form a basis, and in this case the dimension of W is 3.